Hello, welcome to this video where we look at the directional derivative in a deeper manner and we start understanding more about the gradient. In this slide, we want to look at, so we talked about the direction, determining the slope. You give me a point, you give me a surface, and I'm on that surface, and you give me a direction, and I'll be able to calculate the slope in that direction. But what we want to talk about is, what's the biggest slope? What direction should I step in order to get the slope to be as big as possible? It turns out the answer to that question involves the gradient. The direction in which you should step in order to get the direction to be as large as possible is in the direction of the gradient. The actual value, the biggest possible directional derivative, is the magnitude of the gradient at the point that you're at. Okay? And so on this slide, we're going to prove this statement. So what is the directional derivative? It's a dot product between the gradient and a unit vector. The gradient evaluated at your point and a unit vector. When we learned about the dot product, we saw that the dot product has a connection between the angle between it has a connection to the angle between two vectors. And so we found that the formula was that if you have two vectors, you want to take the dot product, you can do that by taking the product of their magnitudes and multiplying by the cosine of the angle between them. All right, great. But what is the magnitude of u? It's a unit vector. Its magnitude is 1. All right, great. Now, we won't know the theta. Okay, we have to figure out why the theta corresponds to the gradient. Okay, the magnitude of the gradient is a number, and so if we're going to maximize this directional derivative, it's going to come from this cosine theta. What would make cosine theta as big as possible? Cosine theta is as big as possible when you get out a 1. Okay, it'll be maximized when cosine theta equals 1. Cosine can't get any bigger than 1. And so if we're interested in maximizing the directional derivative, we need to have cosine theta equal to 1. And then if it is, look at the calculation now. Mag u was 1, cosine theta was 1. So the calculation says that the maximum value of the directional derivative is the magnitude of the gradient. There were 3 parts to that product, and 2 of those parts were both 1s in order to maximize the directional derivative. Now let's talk about this theta. Now theta is an angle that's between 0 and pi, the angle between two vectors. Okay, so you have your unit vector and you have your gradient vector. What angle between 0 and pi makes cosine equal to 1? And that angle is 0. And so since the cosine must be equal to 1, theta must be equal to 0. What does it mean for the angle between the vectors to be 0? It means that they are pointing in the same direction. The unit vector and the gradient vector are pointing in the same direction in order to maximize your directional derivative. So that proves the statement that not only is the maximum value of the directional derivative equal to the magnitude of the gradient, but the unit vector, or the direction in which you should step in order to have that maximum value, is in the direction of the gradient. All right. We talked about maximum. Why can't we talk about minimum? And so take this whole argument and replace the cosine theta being equal to 1 to the smallest value when cosine theta is equal to -1, and you'll have the opposite statement. If you want to step in a direction to decrease as fast as set. So increase, you're headed up the mountain, and decrease, you're headed down the mountain. If you want to head down the mountain as quickly as possible, you want to step in a direction that's opposite the gradient. Why opposite? Well, how can cosine theta be equal to its smallest value, who is -1? What angle between 0 and pi would make cosine theta equal to -1? It's pi. And so the angle between the unit vector and your gradient vector should be pi. But when the angle between two vectors are pi, they're pointing in opposite directions. So if your unit vector is pointing, if your gradient vector is pointing this way, then opposite it should be the direction in which you want to decrease the fastest. So the opposite of the direction of the gradient will be the direction of maximum decrease. All right, great. So the gradient is used to calculate any directional derivative. If you want the biggest directional derivative, you use the gradient. All right, great. There's more to the gradient. If you have a multivariable function and you slice it with the plane, let's do three-dimensional function, slice with a plane z equals k, then the intersection between your surface and your plane is a curve. Okay, that curve is called a level curve. Okay, it turns out that the gradient is perpendicular to every level curve. Okay, so no matter what altitude you're at, if you actually have a bunch of altitudes and you collapse them onto one graph on the XY plane, that's called a contour map. And if you want to look at then the gradient, you can then say that I don't care what the curve looks like, my gradient will always point perpendicular to the curve. Now, to be perpendicular to a curve is to be normal. The word is normal. You got tangent to the curve, and then normal is perpendicular to, or orthogonal to tangent. And so the gradient points perpendicular to the level curve. All right. All right, wonderful. So if you slap these all down into one graph, have a contour map, then you can use the gradient. Remember how it gives you the maximum rate of increase? You can use the gradient to figure out your path that'll give you the steepest path of ascent. The ability to be able to get to the top of the mountain as quickly as possible would follow along gradients. You can map out that path by drawing in perpendicular lines to your level curves. All right, great. Let's not add that to this next slide, to the next video. There's going to be one more use for the gradient that we're going to talk about before we jump to the next section. If you want to find the equation of a tangent plane, you actually use the gradient. It turns out that the gradient, on top of all the other things we said, it also is the normal vector for the tangent plane. And so we'll prove that. We'll do some examples. It depends on how the function is given to you. The function can be given to you implicitly with the x, y's, and z's all mixed in, or the function can be given to you explicitly with z as a function of x and y, the normal kind of way. And so we'll look at both ways, and they both involve the gradient. All right, thank you for watching. My name is Nakia Remmer. I'm here to help you through this multivariable calculus journey. Please like and subscribe or comment down below. Reach out to me if you have any questions. This is my way of being able to explain, and hopefully in a manner that you can understand, in short videos instead of one long lecture at one time. If you want extra resources, you can find them on my webpage, CalcCoach.com. I have like a solutions manual to my midterms. I have also my notes. If you want these notes as a PDF, you can find them there. All right, thank you very much. I'll see you in the next video.